In this tutorial, I'm going to cover silicon diodes, bridge rectifiers, and how you convert AC to DC. Here's the schematic symbol of a diode and a picture of the real thing. The little stripe on the end of the diode tells you which way to put it in your circuit. But what is a diode? A diode is a device that only allows current to flow in one direction. A helpful way of remembering this is to compare diodes to water valves that only allow water to flow one way. So if you feed an AC voltage or current through a diode, the negative voltage will just get blocked off, and you'll be left with only the positive half of the waveform. This process is called half-wave rectification, and it doesn't have to be with just a sine wave. It'll also work with square waves, triangle waves, or any other waveform that dips into the negatives. Wait a minute. If you zoom in and put the waveforms on top of each other, there's a voltage missing. Well, that's because there's no such thing as a perfect diode. All diodes will have what is called a forward voltage drop, or VF. This means that whenever current is flowing forwards through a diode, there will be a voltage drop of usually around 0.7 volts. The exact number will vary with temperature, current, and the type of diode, but for now let's just say it's 0.7. So a silicon diode won't even turn on until there's 0.7 volts across it, and after it's turned on, there will always be that 0.7 volt drop across the diode. Check out these examples to see what I mean. With a negative voltage on the input, the diode can't turn on, so you get nothing on the output. With 0.3 volts on the input, it's still not enough to turn on the diode, so again you get nothing. With 0.9 volts on the input, it's just enough to turn on the diode, but because of the voltage drop, you only have 0.2 volts left. And with 10 volts minus 0.7 volts, you get 9.3 volts. Now, sometimes that forward voltage is a problem, sometimes it's not. For the example I was showing you here with the 10 volts peak-to-peak on the input, it was almost unnoticeable. But if I was trying to rectify half a volt AC, like the signal coming out of my MP3 player, that 0.7 volt drop becomes really annoying and it doesn't really work. You'll have to use advanced techniques like superdiodes to deal with it, but you don't need to worry about that for now. Now, nothing is ever 100% efficient, so let's talk about power ratings. How can you predict whether a diode is going to melt on you? Well, the power wasted in a diode is given by VF times the current flowing through the diode. So for an ordinary silicon diode with a VF of 0.7 volts, with 1 milliamp flowing, only 0.7 milliwatts are being lost to heat, so who cares? But at 3 amps you're generating 2.1 watts of heat, which is quite significant, so you'll either have to use a bigger diode or use a diode with a lower forward voltage like a Schottky diode, and I'll cover those in another video. Incidentally, no matter what anyone tells you, you cannot reliably put diodes in parallel for more current. What happens is one diode ends up doing all the work, and the others just end up heat-sinking the other diode. The last non-ideality that I want to talk about is diode switching speed. The 1N4007s I'm using here are designed for low-frequency power electronics, like the 50 to 60 Hz AC in your homes. Now, watch what happens when I increase the input frequency. After about 15 kHz, the diode becomes useless because it starts conducting backwards. This is because it takes a certain amount of time for the diode to switch between allowing current to move forwards to blocking any current trying to move backwards. Different diodes will have different switching speeds, so if I replace the 1N4007 with a 1N4148, things work nicely all the way up to 100 kHz and beyond. For radio frequency applications, you'll want diodes that switch even faster. So, whenever you're designing something, you'll have to think about your diode's maximum rated voltage, the forward voltage, the current rating, and the switching speed. Always Google the datasheet for the diode you're working with. Okay, that's most of the diode theory you will ever need to know, so let's use diodes to build something. The most common use of diodes is to convert AC to DC, to power the different gadgets that you have at home. I'm going to show you how to build simple, unregulated DC power supplies, and one of them ends up being very similar to this one I have here. I'll start with a very simple low current supply, and then I'll show you how to improve on the design so that it can handle heavier loads. You start out by stepping mains voltages down to a lower, safer AC voltage. I showed you how to do that in my tutorial about transformers. With zero load, my transformer is giving me a nice clean sine wave of around 39 volts peak to peak at 60 Hz. Now, when I add in a 1N4007 diode, and measure the voltage before and after the diode, you can see the negative voltage gets cut off. Technically, I have just converted AC to DC with just one diode, because I've eliminated all of the negative voltage. But this isn't very useful DC, is it? Half the time you've got a weird hump-shaped voltage, and half the time you've got nothing. So you're going to need a little more stability than that if you're going to power anything useful. So, we add a capacitor here to smooth things out. I'm starting with 1 microfarad, but the more capacitance the better, because you'll have a bigger energy reservoir. That's more like it. Now I have a perfect DC output of 18.7 volts. Whenever you're creating a DC supply, this is ideally what you want to see on the oscilloscope, a constant, stable voltage. Now, unfortunately, the only reason why things look perfect right now is because I haven't put any load on the supply yet. The capacitor got charged up through the diode, and right now there's nothing that would ever drain that capacitor. So, let's see what happens when I add a 4.7 kilo ohm resistor as a load. Ohm's law predicts that this should only be a 4 milliamp load, which is very little, but take a look at what happens. What you're seeing here is that when the AC input is positive, the diode allows current to flow through, so the capacitor gets charged. But as soon as the input voltage starts dropping off, the diode blocks the backwards flow of current, and the only energy source left is that tiny 1 microfarad capacitor. And as you can see, it gets drained pretty quickly, even under low loads. So what do we do about this? Well, let's increase the size of our energy reservoir so that we've got enough to last us until the next time the input waveform goes positive again. Let's replace that puny 1 microfarad capacitor with a beefier 470 microfarad capacitor and see what happens. Hey, that worked really well. Now we have a DC power supply that will handle a few milliamps, which is enough to power some sensors and op-amps. Okay, let's turn it up a notch. With a 10 ohm load, this circuit should draw a lot more current. Well, that sucks. Now we're back to the situation where the voltage is sagging in every cycle. The average voltage is 8 volts, so we're only drawing about 0.8 amps, and the magnitude of the voltage ripple is just huge. Imagine trying to power something with this. The voltage would constantly drop so low it would never even stay on. So even 470 microfarads is just not cutting it anymore as an energy reservoir. One thing we can do now is take the brute force approach and add even more capacitance. So let's see how the circuit performs with 3400 microfarads. Well, it's better. Now we're getting an average voltage of around 12.5 volts, so we're drawing an average of about 1.25 amps, but we've still got 5 volts of AC ripple, which is a lot. Now, we can keep adding capacitance all day long to reduce the amount of sagging between cycles, but for loads of several amps, it just becomes really impractical and expensive. So take a look at this cool trick. If you take 4 diodes and arrange them in this way, you form what is called a bridge rectifier. It works like this. In the first half of the sine wave, where the top wire is more positive than the bottom wire, these 2 diodes turn on and allow current to flow forward. The other diodes stay off, blocking any possible reverse flow of the current. Now in the second half of the sine wave, where the top wire is negative with respect to the bottom wire, the other 2 diodes start conducting, and the other 2 turn off. So instead of wasting the bottom half of the AC waveform by clipping it and never using it, you just reroute it and flip it around. So on the output, you get DC at 120 Hz instead of 60 Hz. And, just like before, you can filter it with capacitors later on to get a nice smooth voltage. You can buy pre-made bridge rectifiers, but it's also easy to build them yourself. Here's mine connected to my transformer. I made it out of 4 1N4007 diodes, and it cost me about 4 cents. Take a look at how the voltage used to go from positive to negative at 60 Hz, and now it never drops below 0 volts, and instead we get these positive constant voltage bumps at 120 Hz. This is called full wave rectification because we're rectifying the full AC wave. Now let's go back to our breadboard with a 10 ohm load and see how the bridge rectifier performs with 470 microfarads of capacitance compared to the single diode solution that we made earlier. Now we get an average of 11.6 volts instead of the 8 volts we were getting earlier with a single diode. And you can see that's because the bridge rectifier is charging up the capacitor twice as often because we're using both halves of the 60 Hz mains AC cycle. Now think about how much difference that made, given that those extra diodes only cost me 3 cents. Bridge rectifiers might be a little harder to understand, but since they work so well, everybody uses them. Now let's compare the single diode with 3400 microfarads to the bridge rectifier with 3400 microfarads. Now we're getting an average of 13.5 volts instead of 12.5 volts, and we only have about 1 or 2 volts of ripple. In other words, the combination of a bridge rectifier with high amounts of capacitance can turn almost any high current AC supply into a useful high current DC supply. Just keep in mind that your diodes and capacitors have to be rated for the voltages you're working with. So what we've got here right now is basically the same thing as what's inside those cheap little unregulated AC to DC power supplies that are used to power radios, clocks, and other gadgets around the house. You could make a 9-volt version and it could power an old Sega Genesis or Super Nintendo. The final thing that I want to highlight is that these are all unregulated DC power supplies. That means that even though we've successfully smoothed out a lot of the voltage ripple, we'll still have the problem of the average voltage changing under load. With no load, it's 18.7 volts out, and for loads of around 1 amp, you get about 13 volts out. Now, for some circuits that won't matter if they're designed to work with a wide voltage range, but for things like microcontrollers and other digital electronics, they'll want a voltage source that is very precise, and for that you'll need to create what's called a regulated voltage supply, and I'll cover voltage regulators in another video. In the meantime, now you know what diodes do and how to convert AC to DC.